Okay, so today we're going to talk about our last main topic in acids and bases, and that is acid-base equilibrium. But before we do that, we need to explain exactly what equilibrium is. So, most reactions that we have seen so far in this class have reactants and products. Now, to draw a balanced equation, we write the reactants on the left side, we draw an arrow on the right side, and we draw our products on the right side, and we have an arrow. Now, lots of reactions are capable of taking place backwards. They are reversible. So this reaction can happen as well, where if you have too much product, the products can actually break down and reform the original reactants. So, equilibrium, the definition of chemical equilibrium is the state at which the forward reaction rate and reverse reaction rates are equal. Okay, so in other words, for every forward reaction taking place, the reverse reaction is taking place, and if both of these processes are occurring at the same rate, that is what we call equilibrium. So, the acids that we've seen so far, strong acids like HCl. HCl will split apart and form H plus and Cl minus. This is not equilibrium. The reason why it's not equilibrium is because the H plus and the Cl minus cannot recombine in aqueous solution to form HCl. This is a one-way reaction. So one-way reactions do not establish equilibrium. Same thing goes for strong bases. Something like NaOH dissolving to form Na plus and OH minus. This is also not equilibrium as well. So if strong acids and strong bases cannot have equilibrium, they cannot have the forward rate and reverse rate be equal to each other, which ones do? Well, the answer is the weak acids and the weak bases can have equilibrium. So remember that a weak acid, the generic formula for weak acid, we use HB, but it could also be used, we could also use HX, or the second letter doesn't really matter that much. The point is there's an H in front denoting that it's an acid, and that this is not a strong acid, it's a weak acid. So the reaction is weak acid reacts with water, and this latches onto water to form what you know as hydronium. And this guy here, the B minus, is what's left over after the H plus has left. Now, if something with a charge leaves, then it leaves behind something that is charged. So a positive has gone away, so that is why the remaining charge here is negative. The positive, the H plus, attached to the water, and that is why H3O has a positive charge. So this reaction is capable of equilibrium. So at the beginning, this reaction takes place more, but eventually the reverse reaction starts happening, and eventually you get to the point where the forward rate and the reverse rate are equal. That is equilibrium. So, first off, you should know that strong acids, strong bases cannot have equilibrium. Only weak acids and bases can have equilibrium. So that's why it's important for you to know whether the formula of an acid is a strong acid or a weak acid. Okay. Once you look at an equation and you realize that it's an equilibrium equation, meaning that it has a weak acid or a weak base, the next thing to do is to set it up mathematically, because there's some math behind this. So here we're using HB again as our weak acid. The first thing we do is we write what's called the equilibrium expression. And the equilibrium expression is set up to be the products over the reactants. And that is why B minus hydronium are in the numerator, and HB, which is our weak acid, is in the denominator. And the thing about equilibrium expressions is that we do not include liquid or solid states. And because this is liquid, that's why it's not included. So let me rewrite this. The equilibrium constant, K, is equal to the concentration of the products over the concentration of the reactants. Now, if there's multiple reactants, multiple products, then they're both going to appear either in the numerator or the denominator, just like this. So we need to set up this expression because what this tells us, this is what the equilibrium constant, that's what this value of Ka is. The equilibrium or ionization constant, equilibrium acid, equilibrium constant, it goes by a couple names. What it tells us is it's the ratio of the concentration of the products over the concentration of the reactants when equilibrium is established. So ratio of products over reactants at equilibrium. Now, most reactants and most reactions do not start out at equilibrium, but eventually they get there. Okay, so we have this value of K, the ratio of products, and I guess to be more specific, we write little EQs here, EQ. That means those concentrations are at equilibrium only, meaning not initial concentrations. That means this number here is unique. Right? Ka is a value and it is unique for every weak acid. Every weak acid has its own ratio that has to exist at equilibrium. Now this number will change from acid to acid. And if it increases, that means there's more H plus released, which tells you that it's a stronger acid. So for example, if I have an acid 1, and the Ka is 1.0 times 10 to the minus fifth, but then I have acid 2, and its Ka is 1.5 times 10 to the minus third, well, the higher value means that they're both weak acids, but this is the stronger weak acid. And remember, stronger means more H plus is released. Okay. So let's go through some practice. Let's first write the expression for these two. In order to write the expression, we need to write the balanced equation. So the dissociation expression, and this can be written two ways. This can be written with water or without water. So I'll do it both ways just to show you. HNO2 plus H2O. H2O is the liquid form, liquid state. We're going to get H3O plus, and we're going to get NO2 minus. All right, so just to track that, the H and the water formed H3O plus. The NO2 bit is left on its own, and it has a minus charge because a positive charge has left. Okay, so this reaction can also be written without the water, and that shortens the equation, so it would look like this. And H3O plus and H plus numerically are the same concentration, so it kind of doesn't matter which way you write it. You can write it either way. This right here is understood. All right, so our expression Ka is equal to the products, and I'm going to just do this for the first reaction, is H3O plus times NO2 minus. Those are my two products. My reactant is going to be HNO2, which was the weak acid, but I'm not including water because we cannot include liquids and we cannot include solids. This is the Ka expression for the first acid. Let's do that again for a different one. So I'm going to write the shortened version in this case. I'm just going to show this separating H plus PO4 with a -3 charge. Notice how the charge changed. Every time an H plus comes and goes, the charge has to change. So Ka is equal to the concentration of H plus times the concentration of PO4 -3 over the concentration of HPO4 2 minus. That is our Ka expression. Okay, so we have looked at equations for weak acids, and we have drawn the equilibrium expression. Okay. So the next thing to do is to apply this and let these help us solve problems. There's two main types of problems, and I'll go through the different examples of them. But basically, sometimes the Ka value is given to you, and if it's given to you, then it's the H plus that you're trying to find. Sometimes the pH is given, and remember, if the pH is given, that means the H plus is also given indirectly. So if the pH or H plus is given, then you can find the Ka. So it's one or the other. Now, we're going to write our balanced equation, and sometimes we need what's called an ice table underneath, and this will show you the difference between the initial and the change, and I think this will become, it's easier to show you what it means than explain it to you, so let's just put this into practice and do an example. All right, so formic acid, HCHO2. I'm going to write the short equation. I'm just going to write it like this. Here's my balanced equation. Okay. Now, the question here, they want us to find the Ka. If they want us to find the Ka, that means they must have given us either the pH or the H plus concentration, and they did. But first, I need to know what to do with those numbers. So underneath my balanced equation, I write a little chart. It's called ICE, and I stands for initial, C is the change, and E is equilibrium, meaning the equilibrium values. So right off the bat, this right here is initial because that's the starting concentration of the weak acid. So I'm going to put that here. And in ice tables, we only use molarities, right? So it's important that only use molarities in ice tables. Sometimes people forget that and they put moles. If they put moles in there, it's not going to work. Okay, so we began this problem with the initial concentration of the acid. There's none of this at the beginning because our acid has not separated yet. But notice that they also told us the pH. So if they told us the pH, this is the pH value, the resulting pH value, and if it's the resulting pH value, that means it's at equilibrium. That means it goes in the bottom row. So let's find our H plus concentration, 10 to the negative pH. So in this case, 10 to the negative 2.38 is going to be 0.00417. All right, if that's equilibrium in H plus, that means that goes here because that's an equilibrium value, which means our change was plus 0.00417. Now, for the other product, this guy, there's a 1-to-1 ratio, and they both started at 0. So if this increases by this amount, for every one of these that increases, one of these will increase. So that's actually going to be the same number. So these are equilibrium concentrations for those two products. All right, on the reactant side, if we began with a concentration of 0.1 molar, and in order to make some product, the reactant must be used. So this has to be consumed, and it's going to decrease, and the amount that it decreases by is based on the mole ratio. So since this is 1-to-1 here to here, that means this will also decrease by 0.00417, which means this will be 0.0958. All right, So we built this little table here, and the reason why we built the table here is because we needed to know what the equilibrium values are. And the reason why we need to know what the equilibrium values are is because in this expression, the Ka expression, which is this, products over reactants, we now have the values to insert. So we can actually solve for the numerical value of Ka. So 0.00417, 0.00417, 0.0958. Now I can just plug all of those numbers and calculate them. And I get a value of 1.81 times 10 to the minus 4. That is the acid equilibrium constant for formic acid. And so it's kind of a lot of work. These problems can be kind of complicated, so it's important that you practice them a lot and you go through the steps, pretty much the same steps. This was an example where we knew the pH, we had to find the Ka. Like I said, there's other problems where you know the Ka and you need to find the H plus concentration of products. So here's an example of that. Okay. Now, they did not tell us which acid they're working with. So when you don't know the acid, that's totally fine. It doesn't matter. You can just use the generic formula. We'll just use HB. So HB will produce H plus and B minus. All right. Now, we need an initial concentration as well. We're going to say this is 0.1 molar because that is standard concentration. Usually there's an initial concentration given to you in the prompt. In this case there isn't, but I'm just going to use 0.1. So 0.1. All right. There's nothing of this at the beginning. Okay. Now, in a problem like this, we don't know how much product is going to be made, but that's okay. We just use a placeholder for now. We just call X. X, X. And if the product side is increasing by X and there's a 1-to-1 ratio between the products and the reactants, that means the reactants are decreasing by X. And so those are what I have for equilibrium values. Okay. Next step. Write your expression, Ka, and take your products over the reactants. Again, in an equilibrium expression, these have to be equilibrium values, which means they have to be taken from the equilibrium row, the bottom row. Okay. So the Ka value is known. We can do a direct substitution, which means we have 4.2 times 10 to the minus fifth is equal to concentration of X times concentration of X over the concentration of 0.1 minus X. All right. So simplifying this, 4.2 times 10 to the minus fifth is equal to X squared, because X times X is X squared, 0.1 minus X. So at this point, we're going to end up with a polynomial in order to solve for X, which means we need to either work this out using the quadratic equation, or we can use the solver function on the calculator. Solver function is too complicated to show in this particular video, but there is another video that shows you how to use it. But for now, I'm going to talk about the next point, which allows us to do this problem without the solver. When the Ka is very small, we can simplify the calculation. So when the Ka is very small, that means, what small means is that your Ka here, 10 to the negative fifth, and your initial concentration, 0.1, notice how it's on order, it's 4 orders of magnitude apart. Like this would be 1 times 10 to the minus 1, this would be 4 times 10 to the negative fifth. That's 4 powers of 10 apart. When you have a difference of about 3 orders or more, then that means you can ignore the subtraction of x here because the value of x will be so small it's not actually going to change the number much. So we're going to rewrite this, simplifying this. And if we simplify that, then this is not much of a polynomial anymore. We can actually solve for the value of x without using the solver function. So 4.2 times 10 to the minus fifth times 0.1 equals x squared. And now this becomes pretty straightforward. So 4.2, so that's going to be 4.2 times 10 to the minus sixth is equal to x squared. So if we take the square root, we get 0.0086. And remember what we said x was. X was this. So that is our concentration of H+. So if we take the negative log of that value, our pH will be about 2.07. So I know I jumped over the last point about how you know if Ka is small. So when the Ka is 3 orders of magnitude different than the initial concentration, ignore subtraction of x in the quantity. Now notice I said subtraction of x. I don't mean ignore x, that you can't ignore these. This has to be there because you need something to solve for. We just ignored this because this was the modification to 0.1 molar, which would end up being so small anyways. That's why it was safe to ignore it. Okay, I know this is a lot. Let's do another problem so that we feel a little more comfortable. Okay, so this acetic acid problem right here. So acetic acid is, we'll just abbreviate it. We'll just use HB again. So HB, H plus, B minus. 0.1 molar solution, 0.1 molar. That's 0, that's 0. This will be increasing by some value that we'll call x. Same with this. So at equilibrium, we will have those values of x. This will be decreasing by x. So this will be 0.1 minus x. Ka expression. The Ka will be the concentration of H plus times the concentration of B minus over the concentration of HB. We can plug in the values that we have, and we have Ka. So 1.8 times 10 to the negative fifth will be equal to x times x over quantity 0.1 minus x. Now again, we get to that point where we're looking at our Ka value, 1.8 10 to the negative fifth, and we're looking at our initial concentration, 0.1. So 0.1 and 10 to the negative fifth, this is again 4 orders of magnitude apart. So we can rewrite this and simplify it as 1.8 times 10 to the minus fifth is equal to x squared over 0.1. Basically, ignoring this bit right there. And then we can solve. So 1.8 times 10 to the minus sixth is equal to x squared. Therefore, x, which is equal to H plus at equilibrium, will be 0.00134 is our molar H plus, which will be a pH of about 2.87. Okay. It's going to take a lot of practice. Good thing we have lots of practice problems to do this. That's how you solve weak acid equilibrium problems. If this was a weak base, you do this exactly the same way. The only thing is, you remember that the value of x is going to be OH minus at the end, which means you take the negative log of OH minus to give you POH, and then you subtract from 14 to get your pH. Okay, and the weak base will be a different lesson. So we're going to stop this one here because it's running long as it is.